All right, so far in this unit, we've been talking about hardware and the concepts behind it. And what we started looking at was, again, this idea of some of the terminology you need to know, like CPU, ALU, and CU. Quick review. What do those three acronyms mean? CPU, ALU, CU. That was very good, unless you were a person going bah, 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 just now. You did very well. Yes. What about IAS? Ooh. What about the S? What's the S? Okay, so IAS is memory. It's a register. What does the S stand for when we're talking about memory? No. If I want to remember something, I am storage. Okay? A is access, to access the storage. I is a word that means I need it right now. Immediate, right. So it's the immediate access storage, what I need right now, okay? In other words, it's sitting right on your chip, so it's right there. If it's not right on your chip, you're going to have to go for a little bit of a walk over to get your storage from somewhere else. So where else on your computer would storage be other than right in the CPU? In random access memory. Where else? What if that's full? Your hard drive, right, which is often called virtual memory because it's, again, it writes to it and then it erases it, okay? Why is the hard drive a bad place, and I'm putting bad in air quotes, to store data when I'm working on a CPU chip? Why is it slow? Because it's further away, right, that's one reason. Okay, so is RAM. RAM's also further away. But why is RAM faster than a hard drive? And actually, let's use an older hard drive. Because why? Doesn't have to seek. Okay, you're in the right ballpark, but why is seeking, it has to seek it in RAM too.
Because with RAM, you don't have to actually access the memory before or after.
Well, no. Think of the hardware. Why is the hardware slower for? Because hard drives are physical devices, and they have to physically move. Whereas RAM is more of an electronic, non-moving device. Now, in modern computers, we're now moving to solid-state hard drives, which are faster. Because anytime you have moving parts, it is slower physically, and that's why. So, for a CPU to work the most efficiently, it should have the most memory immediately available on immediate access. We also talked about motherboards and daughter boards, if you remember that. And how the word board just means a circuit board, or card meaning a circuit card. Today we're going to talk about the machine instruction cycle. This is what the computer's hardware has to follow to execute your commands, your code. There are several different ways you can think of this, but there's basically some simple wording that can describe it, okay? The simplest would be fetch an instruction, execute an instruction, a two-system cycle, okay? But we could expand that. Fetch, execute, decode. Or fetch, decode, execute. Or fetch, execute, decode, store. So let's just kind of break down what these words mean. To execute means you will run the instruction. So if you said add these two numbers, it will execute that instruction. Decode means to make sense of that instruction. Okay? So it has to find what the instruction means, and possibly if you say add these two numbers, it has to go get the two numbers, right? It has to get their contents to actually execute it. It can't execute. Like if I just said to you right now, add these two numbers, your immediate response to me would be, what two numbers? You would want that information, okay? Which is, again, part of the fetching process. So in decoding the information, you might have to fetch a little more information. If all that information is sitting in the immediate access, that just makes your job easier. If you said to me, if I said, add these two numbers, you said, what two numbers, Mr. Walks? Well, I said, oh, I wrote them down in the band room. Go get them. That's going to take you time to go get those two instructions out of the band room and get back here. If I said, oh, they're right here, you're going to work faster. So the more immediate your data is, the faster you can do that. Okay? CIR, just as a remember, stands for control registers. So that's the instructions sitting in the control unit to tell you what I'm actually going to be doing. So for example, I might give you a message and I say, execute this. And it's just basically this number plus this number. But you didn't know all three of those parts. You're like, well, what's the number? What is plus? And what's the other number? So you get the plus from the control unit. You get the numbers from the immediate access storage to do the instruction and execute it. Okay? So these are the things that you can put into a cycle of, so again, like if you're building a sewing machine, you would lay out the cycle in which it will perform all these operations over and over and over again as fast as possible. Okay? As well, when you're finished your execution, you might get an answer to the question, what are these two numbers added together? You're going to have to take that piece of information and also store it. So let's kind of lay it out in a flowchart. I fetch the instruction from the immediate access storage and I put it into the control information register. I decode it. Okay, what did this instruction say? If I need to, I also fetch any other data, like what the two numbers are. I execute. I do what it said to do, and I store the results. Do I need to go back and do this again, or am I finished this? Stop. This would be then a cycle. This would be where the cycle continues. So as it goes through your code, line by line, and it gets to here, is there another line of code? Okay, go back and do it again. Fetch the next line of code. So now we'll talk in terms of code. Decode what the code means. Decode. Get any information that your code requires. Execute the instruction. Store any results. Am I finished my code? Go back and do it again. So this is a direct translation of the code you write into what the machine actually does with it in what's called the machine instruction cycle. Okay? If we jump back to, actually maybe I'll just go back to what the curriculum said on that. Just to show you again, because I did that last time we looked at the curriculum. I want you to see what the curriculum says about this thing called the machine instruction cycle. Okay? So it's a point in the right here. It says, explain the machine instruction cycle. This should include the role of data and addresses. So we're going to obviously put that together in a second, but it's just this cycle of instructions that the computer is doing with you. Okay? Okay. So let's do this on the projector just a little bit. Let's write some very simple code. We'll do it in Java. Okay? So let's say you said to it, int x equals 5, int y equals 4, int z equals x plus y, etc. That was your actual code. Okay? So the machine gets your code, and now it's at the point where your CPU is going to handle this. And your CPU has a couple parts to it. It has the ALU, which does math. It has the CU, which holds controls. And it has the immediate access storage, okay, which also has different parts to it. It has the control register and other types of registers. But let's just kind of see how this goes. In addition to this, we have RAM, and we have our hard drive, okay, or sometimes just called virtual memory. Because it doesn't actually have to be your hard drive. It can be anything. It can be a flash drive. It can be online storage if you have it set up that way. Once the immediate access is full, it goes to RAM and then it goes to there. So these are these things, okay? You may also recall that the CU and the ALU are connected. And the IAS is also in part of this as well. So all these things have connections. What's another name for the connections of data? What's a better word for it? Buses, right. So this is data being bussed back and forth. Okay? And there's different types of buses, but for now let's just keep that in mind. Okay. So now this is the hardware. Now let's look at that machine instruction cycle. Okay? So let's think of the way it has to handle your code. One, it has to fetch an instruction. So I get this instruction, int x equals 5. What do I need to do next with that instruction? Decode it, yeah. I have to decode it. I have to figure out what it says. I might then also need to get other information. So I'm like, oh, x equals 5. I might have to get more information. So it's possible I'll also have to fetch more information at this point. But this may not be necessary, depending. So I'm going to put that in as sort of part of this cycle. But it's there. I might have to fetch more information, maybe. So maybe I'll put a little green question mark there. Okay, so I've decoded it, I fetched it, now what do I do? So I know what it means, I've got all the info, I got to execute it. Okay? Now, I now have x equals 5. I know what I wanted to do with that line. Think about what that line wants to do. It wants to create a variable and give it the value 5. That's all that line wants to do. So I fetched it, I figured out what it wants to do, I've executed that, which means that 5 now needs to be remembered. So I'm now going to need to store that information. So I'm going to store the value 5 somewhere in probably immediate access, because that's probably a handy place to keep the x right now. Okay? Remember how we talked about we could have someone who can do lots of instructions at once, but is slow, or someone who can do very few instructions, but is very fast. So that's what we have here. We have someone who's really dumb, can't do much, but is really fast at doing them. Now, the cycle part means, once I've stored this, am I done or not? Okay? So I'm going to put done, question mark. If I'm not done my code, I go back and do it again. Okay, I fetch the next instruction. I decode it. I execute it, make something called y and put a 4 in it. I store that. Am I done? No. Let me go back to the next line of code. Okay, find this information, fetch it, decode what it means. Ooh, do I need to fetch? Yeah, I need to fetch x and y to do this instruction, so I fetch them. I execute the result, 9, and I store the answer. And at this point, I'm done. Okay? That's how the hardware combined with the cycle eventually start working on your code. And that's why I love the word decode there. It's turning your code into something the machine can handle. Okay, so that's the machine instruction cycle. The next part of the IB curriculum. Okay, now let's talk about memory. We have to describe the words primary memory, cache memory, and although it's not written here, we're also going to talk about secondary memory. Primary memory, secondary memory, and identify the need for persistent storage. Okay, so let's connect those words to our actual thing we've just been drawing. If I was to ask you, what is primary memory right now, what would you say? Which of the things up here? First of all, I think there's 3 things that are memory. This is memory, and this is memory. I'll underline all the memory in red. Out of the 3 of them, which is primary to you? Right, why? Right, it's right there. It's the most important in a sense for the CPU to work with. So then would this be secondary memory? Could be. They're loose terms to describe kind of what's going on there. Now, if I had a very small amount of IAS, this would be more primary to me, right? And if I had lots of IAS, this would be more secondary to me. So it's not that well defined. It depends on the actual capacity of that. Now, what about the word persistent? When we're talking about storage that's persistent, what are we talking about? Okay, what does that? What remembers something after the computer's been turned off and on again? Okay, but I'm talking about the hardware. Virtual memory? What about a file? When you save data to a file, you're saving it permanently. That's persistent storage. Does anyone also know what the opposite of RAM is? Or, yeah, read-only memory, or ROM. Is ROM persistent? Yes. So when we're talking about persistent storage, we're talking about ROM, stuff that can be written to and it remembers it after the power goes away, and files, which is hard drives and everything else. So these are the words that you want to be familiar with, okay? So let's go back to that curriculum point and let's see what it says. Describe primary memory. Distinguish between random access memory, RAM, and read-only memory, ROM, and their use in primary memory. Explain the use of cache memory. Students should be able to explain that the effect of cache memory in speeding up the system, as well as being able to explain how it's used. Which of the memories in the previous diagram could be called cache memory? IAS. The IAS, right. So different words, but why is that good to have lots of cache?
Because that way it's great data.
And how does that affect your overall bottom line? Makes it faster, yeah. It's going to make it faster. What's the need for persistent storage? To store data in a non-volatile device. Okay? In other words, a device that can survive the power going out during and after the running of a program. Okay? Now you can see here there's social consequences here. For those of you who've done TOK, there's even a TOK consequence here. If there's no consequence of data loss, why is it stored? So there's no such thing as persistent data. There's no such thing as permanent. Yeah, never mind. We're not going to get into that. But you can see there could be philosophical positions on this. All right. So here's what I have in the notes on this, on primary and secondary memory. Primary is main memory, which stores the instructions and the data in binary code. The control unit deals with the instructions, and the ALU unit deals with the calculations and comparisons. Now, actually, that's a quick note there. Calculations and comparisons. If you think about the code you write, we can do the int x equals 5. We can do int y equals x plus y. But what about an if statement? What calculation is being done there? It's doing a comparison. How could you, if you didn't use an equal sign, write an if statement to check to see if x was bigger than y? X minus y, yeah, is... Yeah, compare them using some sort of arithmetic. And do we have to do subtraction? We can add a negative, right. So that adding that we talked about can actually also be used, if written properly, to actually write if statements and loops and everything else. And as you know, if statements and loops are the building blocks of larger programs. So everything is building off that small starting point. Okay? Data instructions are moved by buses. There's two types of memory. The random access memory, which is a bad name, I admit, okay, which loses its contents after the power is turned off. So RAM is defined as volatile memory, okay? Those are words you should know as well, volatile, because it only survives as long as there's power being provided to it. The memory can be written to and erased and then rewritten to. ROM, or read-only memory, is non-volatile, which means it survives after the power has gone off, okay? Which means it's persistent or permanent data. ROM is used for things like startup instructions for the computer. We generally don't use ROM to store our files, but ROM is used by the hardware for instructions on starting up procedures, okay? The so-called boot instructions, or other types of, one's called the post instructions, power on self-test, post. Okay. When the program's in data files, the software is not in RAM, they have to go to somewhere else. So they start in IAS. When that's full, they go to RAM. When that's gone, then they move to secondary storage devices like tape drives, really, CD-ROMs, disk drives. Sure, whatever you want to call them. From USBs to hard drives, to CD-ROMs. Do you guys even know what a CD-ROM is anymore? To tape drives. Do you know what that? No, you don't know that. To floppy drives, whatever. It's secondary storage at that point, which is a peripheral device. Okay? RAM loses its contents when the power is turned off. RAM can be written in, written to, like a chalkboard. It's like scrap notes. Okay? RAM is just those silicon chips we talked about. With the P silicon and the N silicon, it's just an on-off switch. That's all RAM is a bunch of little switches to remember on-off states. That's all it is. ROM is also that way. It's just a lot of switches. It just keeps the switch in its position after the power goes off. Okay? Obviously, RAM is something you can modify in the purchase price and the upgrade of technology. Okay, I can say computer here, but it doesn't have to necessarily be computer. Okay? A simple analogy that I've given to simple people is the more RAM you have, the faster your computer is. Basically, if you double the RAM, you double the speed. That's not totally true, but it is actually mostly true. That if you have more RAM, you're going to double the speed. If you have more IAS, you're going to even increase the speed more. But you can't modify that at the chip level. That's in the purchase price of the chip. The chips that have more IAS are going to be more expensive chips. Okay? Once the RAM's used up, it goes to secondary. Secondary storage will not affect the speed, generally, unless it's completely different pieces of hardware. Like a hard drive that spins versus a solid state drive, that's going to have a difference. Okay? You guys know what that is? You know what the CD-ROM is? You ever heard of the print shop? No, never mind. Ask your parents, they'll remember that one. Okay, so that's that secondary storage. Okay. When you use secondary storage, there is definitely a latency period or a lag between what your CPU is trying to do and the amount of time it takes to get that data. Okay? So again, if we think of it this way, right on the chip is our IAS, or our cache memory. It's right there. It's easy to use. Okay? You will use this onboard memory to do all the calculations, but if onboard memory fills up, then it backs up to RAM, which is also pretty good. You could absolutely consider RAM primary memory because it is fast and it is close by. Actually, if you look inside any piece of computing technology, the RAM will be right close as physically possible to the CPU. They do that on purpose because there is a limit in speed known as the speed of light. Okay? Once RAM is full, though, then it needs to go to secondary memory, some sort of physical, virtual storage device. And that isn't, first of all, it's not close by. Second of all, it's a slower process to get out of there. Okay? So in a best case scenario, all of our code and all the data we need sits on onboard memory. But as you guys know, you're now writing bigger programs, more complicated programs using dynamic structures like linked lists, which could hold like 7 billion pieces of data. And that data might be complex within itself. So you're going to fill up IAS, then you might fill up RAM, and now you're going to secondary memory, which can cause a lag. Okay? Whew. Okay. So best case scenario, and again, reproducing this type of diagram and talking about the way this data is interacting is a very common IB question, where it says, draw a picture of the CPU, including the ALU, CU, and how data is filters through that system, perhaps including primary and secondary memory. That might be like a 4-point question, and you guys should be able to piece together something to answer that question. Okay? Having a lot of onboard memory is a good thing for speed and processing power. And after that, having as much RAM as possible is a good thing. Now, beyond that, what other type of memory can we have? Well, memory itself comes in like sticks of memory or SIMs, or sometimes it depends on sort of what device you're putting it into. And it can all have lots of different acronyms. Some of these acronyms are a bit out of date. Okay? Cache memory as well can be divided up into different parts of cache memory. RAM can be divided up. So some of this is a little bit old, but even the memory itself can be subdivided into different systems of memory itself. Okay, so what you want is RAM that is obviously high speed, okay, that can access quicker. So within cache, there's something called pipeline burst cache, which allow reading and writing to occur at the same time. So that's like the difference between a one-way highway and a two-way highway, right? If it's two-way, you can both read and write at the same, that's better, right? Then there's different levels of cache memory. So the memory going in there absolutely matters, and memory that can do more and operate faster is definitely more expensive. That being said, the price of this memory has gone down significantly in the last 20 years, okay? Very significantly. I used to actually have an article on the wall about this upcoming new memory, which is now everybody uses, right? But I remember in the early 2000s having that article on my wall. I believe I took it down when I came over to this school. But it talked about this new type of memory, which was going to be USBs. Like this is before USBs in the 2000s. So memory is measured in quantifiable units, usually by the byte, Does anyone remember what a byte of data is? 8 bits. What's a bit of data? Yeah. A bit of data, 1 bit, is basically a light switch. It's an on-off state. Or we usually define it as a 0 or a 1. Does anyone remember what the word bit came from? Binary digit, right. So it's that binary 0 or 1 digit. 8 of them is a byte. Okay. What's a kilobyte? 1,024 bytes. Why is it 1,024 and not 1,000? It's a power of 2, right. Then from kilobyte we go up to megabyte, and then gigabyte, and then terabyte. Okay, I remember saying this to IB classes 10 years ago. We're going to soon have terabyte drives. We're now common, right? We have terabyte drives. What's after tera? Anyone know? Petabyte. You guys are going to live in the era of petabyte. What's beyond that? I don't know. Okay. By the way, there's a word for 4 bits. 8 is a byte. 4 is a nibble. Yes, that's right. Isn't that horrible? Bit, byte, nibble. All right. There's also memory built into your peripherals. Your video card or video board also has onboard memory. So that's just like the CPU, it's handy for it to have its own memory built onto it so that it doesn't have to go get it from secondary memory. So video cards, you could even argue sound cards could have some memory built into it, but it's less of a priority. But with video cards especially, absolutely, because of the amount of data they're processing, it's good to have some onboard memory on there, okay? All right, we're flying through this stuff today. Okay, so this is some pretty simple stuff, operating systems and utilities. An operating system is a program to run other programs, but it's definitely more than that, okay? It manages all of the system itself, including all of its resources. So the most basic function that an operating system needs to do is provide output to the user and take inputs from the user. So it needs basic input-outputs. Have any of you heard of the term BIOS before? Wow, you're Mr. Acronym today, Liam. That's right. BIOS stands for Basic Input-Output System. BIOS is usually built by the hardware manufacturers. The hardware manufacturers say, this is the basic input-output system. On top of that, you can put whatever operating system you want. So Apple, you can put your operating system. Windows, you can put your operating system. Linux, you can put your operating system. Unix, you can put your operating system. Solaris, you can put your... Do you guys know any of these? Never mind. Anyways, if you're Apple, you're building the hardware and the software. So your BIOS, you're not building it for other operating systems. You're like, no, 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 no. My BIOS is for Apple only, okay? Are we going to play the what if scenario? No, we're not. Okay, now, operating systems come in things so that they have these core functions, like basic input-output. That's a core function of the operating system. Managing memory, that's in a core function. It has to do that. Running programs. So if I buy Windows, it better be able to run Microsoft Word or something like that. That's a core function. But then it provides other utilities as well, because they want to make it sellable to you. They want to provide other services like, hey, I can format your USB for you if you want. I can create backup files for you if you want. I can give you solitaire if you want, right? So these are other features that they add on top of it. Early operating systems did not have as many of those. And their basic input-output system was very, very simple, like the machine in the back corner, which was the DOS operating system, disk operating system. It had basic instructions that you typed in, did not provide a user interface for you, okay? Obviously, developments in software have moved to the graphical user interfaces that we're used to now, okay? Here are some ones that you may not have heard of. By the way, what do you think the MS in front of DOS stands for? Microsoft, yeah. What about VMS? Wow, never heard of that one before. Okay. What about OS/2? Any of you ever heard of that one? OS/2 was an IBM operating system. I attended a 1999 thing at the convention center in Winnipeg, which showcased the upcoming operating systems that everyone should buy. They had a giant display for OS2 by IBM and a giant display by Microsoft for Windows 95. And at the time, they were neck and neck because neither had come out yet, and both were being talked about. Now, we know which one, hopefully, out of the two kind of had more survival rates. But if you Google a picture of OS2 right now, you can see the operating system. And in some ways, they were Microsoft was accused of stealing some of the information from OS2. Anyways, I don't want to get into conspiracy theories. Here's a picture. This is OS2, right here. This is the Windows 95 operating system at the time. This is actually, I don't think that's the Mac operating system at the time. That's a little bit of a newer Mac operating system. Okay? And this is Unix. Okay, not Linux. Do you know the difference?
Unix.
Which one came first? Unix. Linux is sort of the operating system they made that would be more available to the public. Unix was built for supercomputers, and Linux was for personal computers. Okay?
Out of all these, the Mac one actually is the most refined.
Yeah, but that's not accurate. That's not an Mac OS from the time. It's I think a little newer. But as you look at some of the comparisons, you can see here that Windows 95 has the traditional start menu, which we have now in Windows 10. We have that same taskbar start system. OS2, I don't know if you can see here, has also a taskbar. It's up top. It has icons, just like Windows does and Mac did. Okay? Unix did not have a taskbar and did not have icons. Okay? It had a different system. It was more command-based. So consumers drove which way these operating systems kind of went, and they continue to in some ways. Okay? All right, I think we'll stop there because we are out of time. And we'll continue this